Now that we're in the possession of this library of functions, together with all of these skills that we have in transforming a graph, how do we put those together in order to sketch the graph of a function that maybe we're not necessarily as familiar with? In this example, we're asked to sketch the graph of a cube root function. We recognize that this is a cube root function because we see a cube root here and then a bunch of linear stuff. So since we recognize that this is a cube root function, we know that the basic shape of its graph is going to be something like this, that sort of S-shaped curve that's on its side. And we know that we want to work with the key points, -1, -1, 0, 0, and 1, 1. And from there, we can just go about unraveling the transformations on this graph. Our first transformation, we see an x minus 1. That's going to be a horizontal translation, 1 unit to the right. In other words, we'll replace each x coordinate with x plus 1. So x is -1 becomes x is 0. X is 0 becomes x is 1. X is 1 becomes x is 2. And we haven't touched the y coordinates yet, so we just copy those. Next, well, we don't have any horizontal scaling. So next we'll proceed to our vertical scaling. Our vertical scaling will also include a reflection. So actually, we're not going to have this curve. It's going to be upside down. We're going to have vertical scaling by 3 and reflection. Our y coordinate is going to be replaced by a -3 times our y coordinate. -3 times -1 is +3. -3 times 0 is 0. -3 times +1 is -3. And now we leave our x coordinates alone, because we're only affecting the y coordinate at this step. And then our final transformation, we have this +2 outside the third root function. And so our y coordinate is going to be replaced by the number that's 2 more than that. So 3 plus 2 is 5. 0 plus 2 is 2. -3 plus 2 is -1. And we leave our x coordinates alone. So our 3 points on our graph will have 0, 5 on our graph, 1, 2, and 2, -1. Now if we just drew those points, we could draw a straight line through them. But because we know we have a cube root function, we also know that our graph is going to have that kind of swoopy S shape. And because we know that we scaled vertically by 3, we know that we're going to make it go through these points by stretching it out real tall and narrow, like this. So we also reproduce the general shape of the cube root of x graph in order to capture more information than just those points would show us. We'd also like to give its domain and range. Because this is a cube root function, the base function's domain and range is all real numbers. We know that transforming all real numbers doesn't change it. So we know that the domain of f is all real numbers, and the range of f is also all real numbers. Okay, so that was one use of the library. Sometimes it isn't obvious at a glance which member of the library we're looking at. and we need to bang on it a little bit with an algebra hammer. This function, for example, is not obviously one of the functions in our library. But we notice that we have that x minus 4 in the denominator. If we could somehow not have an x in the numerator, well then this would be a member of that 1 over x family. But thinking a little bit further, we have a tool for expressing a function that looks like this in terms of a number over x minus 4 plus a polynomial with degree less than the numerator. And that's long division. When we encounter a rational function like this and we want to sketch its graph, our first move should be, if the degree of the numerator is at least as big as that of the denominator, to do division. This denominator is in the form x minus a number, so I can use synthetic division. Take the opposite of the negative 4, use positive 4 in synthetic division. You can do that way. Just because we haven't seen it for a while, I'm going to use regular polynomial division. So we're going to divide x minus 4 into 3x minus 10. And looking at just the leading terms, x goes into 3x 3 times. 3 times x is 3x. 3 times negative 4 is negative 12. We subtract, and we get positive 2 as our remainder. Our function is g of x equals 3 plus 2 over x minus 4. Oh, well then, if we say f of x is 1 over x, g of x is, let's see, this term is 2 times f of x minus 4, and then this term we're adding 3. So that means we're transforming the graph of 1 over x. Let's see. When we transform the graph of 1 over x, we'll use the points -1, -1, and 1, 1, and then the points x equals 0 and y equals 0 will be relevant to our domain and range. What transformations do we have? Well, inside the function we have x minus 4. That's a translation, 4 to the right. So we're going to replace each x coordinate by x plus 4. So -1 plus 4 is 3. 1 plus 4 is 5. 0 plus 4 is 4, and we're not going to touch the y's. 0 plus 4 is 4, and we're not going to touch the y's. So our points are now 3, -1, 5, 1, x equals 4, and y equals 0. Our next transformation, we have multiplication by 2 outside. So each y coordinate is going to be doubled. So -1 times 2 is -2. 1 times 2 is 2. We're not touching x's, so we're not going to touch x equals 4. And 0 times 2 is 0. So we still have y equals 0 here. And then we copy our x's. Our last transformation is this plus 3 which is a transformation upward by 3. So we have y replaced by y plus 3. Negative 2 plus 3 is 1. Positive 2 plus 3 is 5. Not touching the x's. 0 plus 3 is 3. Leave our x's alone. So we'll have our vertical asymptote at x equals 4. We'll have our horizontal asymptote at y equals 3. We'll have one point at 3, 1, and another point up here at 5, 5, right at the edge of our graph. And then we'll sketch the general shape of the graph of 1 over x, stretched vertically. And we have a rough sketch of this function. If we wanted a nicer sketch, we could fill in some more points, but this gives us the general shape of the function. We can also say what the domain and range are, because these are the points that are not in the domain and range. So our domain is the set of all x's that are not 4, and our range is the set of all x's that are not 3. So just by the transformations, we also see what the domain and range are, since we knew the domain and range of the original function.